Hello and welcome. In this video we're going to analyze the final form of the second order linear differential equation, which is the non-homogeneous second order linear differential equation. So far, and even in this lesson, we're going to focus on the differential equation that is, roughly speaking, of the form second derivative plus some function of some constant. I think we maybe have written some function of t, but we're just going to focus on the situation where that coefficient of dy dt is a constant. So I won't put g of t there, I'll just say g plus some constant times y equals 0. So that's what we've been focusing on, but in order for this to be non-homogeneous, we have some sort of function over here. Now we are referring again to these coefficients as being constant, and therefore we often refer to this as a non-homogeneous constant coefficient second order linear differential equation. So kind of a long term, but this makes it a very specific situation. So if these are functions, this method will not necessarily help us get any farther. But moving forward, we considered the spring mass model, which had two main forces. One was the force due to the spring, and so recall we have some sort of spring here, some sort of mass attached to it, and wherever we have displaced this spring relative to rest, so let's just say that that represents y equals 0, which is at rest, then if this spring becomes stretched out, then the force of the spring wants to act in the opposite direction of the displacement. So it's going to want to go that way. Similarly, if we compress this spring, then the spring is going to want to push it the other way. So there's this negative proportionality. And as we know, the farther you stretch a spring, assuming it doesn't distort, the more that you can feel that force getting stronger and stronger in the opposite direction. So the more displaced that spring is from rest, the bigger the effect of that spring force. Damping force is similar, but that's negatively proportional to velocity, meaning that if this mass is moving downward, the damping force is slowing it down. A harmonic oscillator can also have this thing called a forcing function, so this f of t over here, which essentially means that there's some superficial force applied to the system. So consider when you, if you've ever seen mattress testing, they take the mattress, imagine this is the mattress, and they have some sort of roller, some overhead roller that rolls this thing back and forth and applies pressure to those springs inside of that mattress. Also, think about the force of gravity. So this could be the force of gravity acting on the mass. So we're going to refer to this new force, f sub force, as some function, potentially of time. It could be constant. So our spring mass system starts to look like this. The right-hand side is non-zero, so this f of t makes this equation non-homogeneous. So to solve this, it turns out that we can already use some principles that we've learned, and this theorem, called the extended linearity principle, is what we get to apply here. So the beautiful part about this theorem is that as long as the equation is non-homogeneous and it has to be linear, we can apply this theorem. So let's just kind of state this. Suppose we wish to solve the above differential equation. If y sub h of t is a solution to the homogeneous differential equation, so set equal to 0, and y sub p is a particular solution to the non-homogeneous equation, so the only difference between these is that this includes the f of t in there, so we have to find the solution, the general solution to this homogeneous version of the equation, and then we find a guess, oftentimes by observing the structure of f of t and then formulating our possible guess for y. Then we can sum these together and we get our general solution for that differential equation. So solving the homogeneous version can be done what we've already done, and solving the non-homogeneous equation, we'll use the method of undetermined coefficients. We kind of guess the general form of a solution, and then we solve for that unknown. So let's take a look at an example. So here we already have the system built with the spring force, damping coefficient, mass, and the right-hand side is mass times acceleration. So this is gravitational force. And here we have initial condition, so the spring mass system is at rest, but it is actually moving into a compression because the velocity is negative, and the mass is 10 kilograms, and we'll assume that the gravitational constant is 9.8 meters per second squared. So if you multiply kilograms times meters per second squared, you get units of force, which is in newtons, which is exactly what all of these should be in. The artificial forcing function is the force of gravity on an object that has a mass of 10 kilograms near the surface of Earth. Okay, so that means that the first thing that we're going to do is we're going to solve the homogeneous version. So the homogeneous version will just be the second derivative plus 3y prime plus 2y equals 0. And so we already know that our solution to this is going to be of the form e to the rt, where r is unknown at this moment. So method of undetermined coefficients will help us find that. And the reason we know that this is a solution is because this is the only function, can't be sine or cosine, because if y is sine and the first derivative is cosine, and those two will never add up and combine to give us 0. But e to the rt, when you take its derivative, you get r e to the rt, and you take its derivative, you get r squared e to the rt. And now making our substitutions in this equation, we have y double prime plus 3y prime plus 2y equals 0. And so once again, we can factor out e to the rt and see that the only way for this left-hand side to equal get a 0 product is if r squared plus 3r plus 2 equals 0. Now we can solve that however we want, quadratic formula, but if we do factor this, which of course this one factors nicely, they don't often do this, it factors into r plus 1 times r plus 2 equals 0, so r equals -1 or r equals -2. So what we've referred to as y sub h, our homogeneous solution, is k1 e to the -1t plus k2 e to the -2t. And this gives us two solutions, e to the -1t and e to the -2t, but by the superposition theorem, we can sum those two solutions to a homogeneous equation, and that forms a new solution. Now the non-homogeneous version. So now we need to consider the situation where the right-hand side is non-zero, and mass times acceleration, 10 times 9.8, will give us 98. So solving this now requires me to find a function that when I take its second derivative, I add 3 times the first derivative to it, and then add 2 times the original function to it, I get 98. Well, the only way for that to happen is y cannot be a function that is anything but a constant. And here's why. Let's suppose we let y equal t. Okay, well, that's already a problem because now I have 2t here, and then its derivative is equal to 1, and then its derivative is equal to 0, so 0 plus 3 plus 2t will not give me 98. So my guess cannot have a t in it. Same thing for like t squared. Well, that means I'm going to plug in t squared here, 2t here, 2 here, and there's no way that a constant plus a linear plus a quadratic will add up to 98. So the only way for this to happen is if y is equal to some constant. So let's go with it and see where this leads us. So that means that the first derivative will be 0, the second derivative will also be 0, and now when I substitute in my guesses, I have 0 plus 3 times 0 plus 2 times a constant equals 98. Perfect. So as long as the constant is 98 divided by 2, which is 49, this will be a solution. Okay, so that means that y non-homogeneous, which we'll call y sub p, this is a particular solution. There's no arbitrary constant that can be attached to this. The constant has to be 49. So you can just double check your work here. 2 times 49 plus 2, 3 times 0 plus 0 is 49. So our general solution will be y equals yh plus yp. And so y is going to equal k1 e to the negative t plus k2 e to the negative 2t plus 49. And we could always check our work. We could take the first and second derivatives of this and plug it into the non-homogeneous equation that we're trying to solve in the first place and see that it makes everything work out. So there's our general solution. Now, of course, we want to satisfy some initial conditions. So in order to do that, we know that our initial position, our position function is this one. I'm going to need the velocity function as well because I have an initial velocity condition. So y prime is going to be negative k1 e to the negative t, derivative of that first term, minus 2k2 e to the negative 2t, and then plus 0. So I know that my initial position is 0, and what we know is when we plug in 0 for the t's, we just get k1 plus k2, and then plus the 49. For the second equation, we're going to get negative 1 is our initial velocity, equals negative k1 minus 2k2. And we'll use Wolfram alpha to solve this and see what we come up with. And so when we insert this into Wolfram alpha, we get k1 equals negative 99, k2 equals 50. So we're now prepared to write our final solution, which is y equals k1 e to the negative t plus 50, which is k2, e to the negative 2t, plus 49. Now we want to see how this thing behaves and to see what happens. So let's go ahead and graph it. And we get something pretty interesting here. So initially, our spring mass system is completely uncompressed, meaning that at time 0, the position of the mass is at rest. Now, we know that we had an initial velocity that wanted to compress the spring. But the interesting thing is that the spring doesn't compress. It, in fact, stretches, and it actually stretches out to about 49 in the long run, meaning, and this is assuming a very elastic system. This doesn't have to be an actual spring in a mass. This could be some sort of vibration. So let's think about what's happening here. Let's kind of sketch this out. So we're saying we have this mass attached, and what's happening is this thing is attached right now. It's perfectly at rest. The initial velocity is wanting to compress this thing at a rate of negative 1 meter per second. But that's not a very, that's a pretty rapid speed, I suppose. However, let's think about the fact that we essentially have a force on top of this. So maybe what we've done is we've put some sort of 10 kilogram weight on top of this. So if I sort of put this 10 kilogram weight on top of this mass, well, the spring wants to pull this thing back up, but it probably is the case that the upward velocity just isn't enough to overcome the effects of gravity. So this thing has potential to want to compress, but what actually happens is this thing slowly droops down, and what happens is it comes to a new resting point where it ends up being 49 units of stretch. So basically this thing is going to kind of slowly inch its way down, at first kind of rapidly, and then it'll slow down and come to a stop. So not a very interesting spring mass system. We have too big of a mass on there, and we could also analyze what would happen if we had different spring constants, etc. Now, one of the cool things to pay attention to is that the only difference between this solution and the solution for the homogeneous version that has no gravity assumed is if I take away that 49, now what happens is that, my initial conditions are off now, so that's something to consider. But now the spring mass system will return to rest regardless of the initial position. And the reason that's going to happen is because now it doesn't have the effects of gravity, it just has the effect of the damping attributable to any damping forces such as friction, etc. But now that we have gravity considered, its natural resting point of the spring mass system is 49 units of stretch. So hopefully that seems somewhat intuitive.